Hi, I'm Tran, and I'm from the Institute of Mathematical Stochastic at Göttingen University. And today I'll give an overview about Fréchet means and its connection with geometry. So first, let us look at the setup that we'll be interested in. In our setup, we will have a metric space MD, and M is required to have some tangent structure. So ideally, we would think of M as a Riemannian manifold, or we can glue some Riemannian manifold together to form a so-called Riemannian stratified space. And a key property that we would want from our stratified space is that the logarithm map and the exponential map are defined locally. So an example of a Riemannian manifold would be a sphere or an ellipsoid. And a simple example of a Riemannian stratified space would be an open book, where we would glue half planes together along the spine, as we see here in the right picture. And after we have our space, we will want to equip our space with a probability distribution mu. And then we will have n IID sample, x1 through xn from mu. Then we can define the empirical distribution mu n. And from mu and mu n, we can define Fréchet functions. So a Fréchet functions is an integral of 1/2 of the square distance functions from a point x. If the integral is again is the distribution mu, then we call the function Fréchet population Fréchet function, or just Fréchet function. If the integral is the empirical distribution, then we call the function empirical Fréchet function. When we have the Fréchet functions, we will look at the Fréchet means of the function. So the Fréchet mean is the minimizer of the Fréchet function, and it's denoted by mu bar. And we always assume that that Fréchet mean is unique. And we also look at the minimizer or Fréchet mean of the empirical Fréchet function, and that will be denoted by mu n bar. So we can see there's an example here in the picture when we have M to be a sphere, and we have a distribution on the shaded part. It is uniformly distributed on a capped in the lower hemisphere and in the strip near the equator. So if the cap is big and the strip is thin, then the Fréchet mean is unique at the south pole. So then when we have the setup, we have the sample, we can compute the sample means. Then we'll look at the central limit theorem of the Fréchet mean. So essentially it is a theorem saying about the behavior of the empirical Fréchet mean as we looked from the population Fréchet mean. So we have mu n bar as the empirical Fréchet mean, and we map it to the tangent space at the population Fréchet mean through the logarithm map. Then we get a vector. But that vector is very small because mu n bar will converge to mu bar. So we have to rescale it by multiplying it by n to the power of 1 over 2r minus 2. And r will be called asymptotic convergence rate. And it will converge to some distribution, h apply to a normal distribution. And h is a process that we will have to look at. So for example, when we have Euclidean space, then the asymptotic convergence rate R will always be 2. That means we have to rescale it by a magnitude of square root of n because the vector is very small. And h mu is the identity map. It doesn't do anything. And n is a normal distribution. So when M is the Riemannian manifold or stratified space, then of course we do have the classical case, but we do have non-classical cases where we have R is greater than 2. That means we have to multiply not by square root of n, but for example, n to the power 1/4, because the vector is now very big. And H is not the identity map anymore. Or we also have non-classical case where we cannot define R, right? Because H will collapse everything into a single point. So the distribution on the right will be a single point, and mu n bar will be at the population mean mu bar after some large n. So there's no rescaling here. So then our question would be, well, what would be the cause that caused the deviation of the central limit theorem from being classical? And if we know the cause, then what information should we expect from this sampling process, right? So to understand that, we have to look at the process of obtaining the central limit theorem. So the regular process would be we start with mu n, right? Then we compute the Fréchet mean of mu n. So that would be the empirical Fréchet mean. So in that process, in this graph, or in this diagram, we go vertically. We start at mu n, we compute intrinsic mean, mu n bar, and we map it to the tangent space at mu bar by the logarithm maps. So that means we take means before taking the log map, right? And that process is called intrinsic sampling. The second process, though, we can do it simpler. We get mu n's, we have n sample points, and we can map those n sample points to the tangent space at mu bar via the logarithm map. So now we have n sample points on the tangent space. We can take the means of the Fréchet mean of those, which is then just taking average. And that's very simple. So that process is taking means after the log map, and that's what we call Euclidean sampling. And that process will give us this notation, and that process will give us the Euclidean central limit theorem. And so we know that there are two processes we can do. An easier one is the horizontal, the harder one is the intrinsic one. And the thing that connects the two will be the map we call H mu. And we see that H mu is the map that corrects the intrinsic central limit theorem from being Euclidean. And that will be the object that we will focus on. So we look at some different cases where we know what H mu is. So first we have M to be a manifold, then H mu will be the inverse of the Hessian of the Fréchet function at the population mean. And that is when we have the classical case. Well, in some case, we don't have the classical behavior. That is when the Hessian vanishes. So we have to look at higher derivative. And that's when we call it Smeary case. So for example, when M is Rn, then the Hessian of the Fréchet function at the Fréchet mean is always the identity map. So H mu is always the identity mapped. When M is negatively curved, then the Hessian will be greater than the identity. That means it will expand vectors. So H will shrink vectors. So it is a contraction map. And as you can guess now, when M is positively curved, then the Hessian will be smaller than identity, right? That means it contracts vectors. So H will expand vectors. Well, as we can see, right, well, we can guess, because the Hessian will collapse or contract vectors. There will be cases where it collapses everything into zero. So that means H can explode. That's why we cannot look at the Hessian anymore. So we have to look at higher derivative of the Fréchet function. So that's the case on manifold. And we see that H mu has close relation to curvatures on the space, right? So now we can give a summary that is, we have different cases of behavior of central limit theorem. So first is a classical case when we have the Hessian of the Fréchet function is invertible. So H is just the inverse of that Hessian. And we have Smeary case. It's when the Hessian is not invertible. So we know that we have some positive curvature because H will link to positive curvature. And then we have to look at higher derivative of the Fréchet function. And we can define H mu accordingly. There will be case where I mentioned earlier, that is when the distribution is singular, or the limiting distribution is singular. That's when we call sticky. There are some examples of this, but essentially that is when mu bar is a singular point and we cannot compute derivative tensor. And H mu will be a projection, so it's not a linear map anymore. So we were left with two questions. First is what kind of information about curvature of M that we can get from the sampling process. And two, well, if M is a stratified space, then is there anything that's similar to curvature or singularities from M that we can get from the sampling process? And that is the end of my presentation. And thank you.